Somebody is trying to read the cylinder number 11. Okay, so I have a picture here actually. So somebody is trying to read this one. This is 1. Somebody is trying to read this one. Then say that. Then while I am doing that, other processes they started. They wanted to read cylinders 1, 36, 16, 1, 36, 16. So 1 is this one, 36 is this one, and 16 is this one. What else? 16, 34, 9, 12. 34 and 9 and 12. These are the orders, okay? So since I am doing this first come, first served, I am going to do this one first, 1, okay? This is the first one. Then I am going to read this one. So this is what I am going to do. Read this one, go there, then I am going to have to go all the way to the other end, 3, then I will have to go back to 4, then 5, then 6, then 12, okay? So this is what my head is read head is doing. So very inefficient, right? It is very inefficient because it is doing first come, first served. Which might be good if there is only a single process running, okay? Because single process needs that data, and if there are no competing read requests, then this is good enough, okay? So that's why people don't use this first come, first served algorithm on multi-program systems. If I do that algorithm, I need to move my drive head for 111 cylinders. I mean, if you measure the distance on this red line, it corresponds to 111 cylinders. Okay. One alternative algorithm would be, instead of doing first come, first served, do this shortest seek first. Okay. So if I am at here number 1, 11. Okay. If I am at here number 1 at 11, then the closest to me is, okay, from 11 to 12, right? I am going to go to 12. Okay. After 12, the shortest one is go, okay, 6. Then shortest one is then 4. Then this one, and this one, and this one. Okay. So it doesn't do first come, first serve. It is trying to reach the closest cylinder that I want to reach. Okay? So it is not doing in order, but it is saying that which one is closer, I am going to do that. So this is much better than the previous one. This is much better than the previous one. Okay. So if you measure the amount of cylinders visited, it is 61 cylinders, almost 2 times better, right? 2 times better, much better performance with this one. Okay, so this is called shortest seek first. It is not first come, first serve. But there is a very serious problem with this one. Can you guess the problem with this approach? For some unlucky processes, there is a problem. I mean, overall performance is good. Okay, overall performance is good, but there is a problem for some unlucky processes. If I have many requests, complete the rest of the sentence. If I have many requests, çok fazla sayıda istek var diske erişmek için. Bir sürü bekliyorlar. 20 tane gelmiş. Bu ne yapıyor? En yakın kimse oraya giriyor, değil mi? Ne gibi bir problem olabilir burada?
Hepsi bir bölüm.
Ya şimdi çok fazla varsa beklediğim nedir? Şu benim silindirlerim olsun. Tamam mı? Böyle bir sürü var. Çok fazla istek geliyorsa random dağıtılmıştır, değil mi bunlar? Böyledir. Ve sürekli de geliyor. Ben ne yapacağım? Buradakiden buraya geleceğim. Buradan buraya geleceğim. Sonra yenileri gelecek. Buraya geleceğim. Yani sürekli ne oluyor? Ortada kalıyor. Çünkü bir şeyler geliyor. Şu sonlardaki, so these requests at the end of the cylinders the highest number cylinder and the smallest number cylinder will never get any chance to be served, right? So they will starve. And we had similar problems with the process scheduling, right? And if you don't prioritize stuff, then some of the processes they will get delayed and they will never get served. People realize that they have exactly the same problem with the elevators of the tall buildings. Okay, let's say this is a tall building, okay, and I have an elevator on it. Let's say 100 levels, 100 stories, okay. If somebody calls the elevator here and there and there and there, so if you go to the closest floor that calls the elevator, you go there and you go there, and you keep going to the closest levels, right? So at the top level, you will never have any chance to go to the top level because people keep pulling your elevator from the lowest level. That's why they invented this elevator algorithm. Okay, this elevator algorithm. Okay, it does this. It doesn't care. It doesn't do first come first serve. It doesn't care about the closest one. All it does is that the cylinder head moves this direction, then it goes this direction. Okay, then it goes this direction. It only goes up or down. Okay, so while it is doing up or down, it picks all the requests on its way. Let's say it started from 11. Okay, from 11 we have 12. Okay, it's going up. Then it goes that way. Then it goes all the way that way and this way. At this point, it knows that there is no request from the top of the elevator. Then it goes this way. Okay. So in this case, it visits total of 60 cylinders. A total of 60 cylinders, which is a little bit lower than the 61 cylinders that the shortest seek first did. This is by coincidence only. I mean, the performance-wise, shortest seek first is better in terms of the number of cylinders visited, but this one is more fair for the processes that wants to reach to the end of the drive space. Okay, yes?
Hocam hangi tarafta daha çok varsa o tarafa doğru okuyup geri gelsin.
Maybe you could use that approach, but once you have your direction set, you should go all the way and all the way to the end of that direction. Okay? You cannot reverse your direction without going to the end. Okay? You could do that too. There is another approach. In that approach, your cylinder head moves only in one direction. Okay? It goes to the up. Once it reaches to the up, it immediately comes back to the beginning and it goes to the up again. There are these kind of approaches. As I said, this is not better in terms of number of cylinders visited from the shortest seat first, but this is more fair. Okay, all the processes get their fair share. Okay, other questions? Okay, good. The elevator algorithm. They are using exactly the same algorithm with the elevators on the tall buildings. Okay, tall buildings, they use this algorithm. So the software maintains one bit. Okay, the bit 0 means up, 1 means down. So when a request finishes, if it is up, the arm or cabin is moved to the next highest pending request because it is moving up. Okay, so it is doing maybe shortest seek in the same direction. Okay, it doesn't move its direction. Once, if there are no requests pending at the higher positions, if it is going up, then direction visit reversed and it starts doing the down. If there are no requests, then your elevator or the drive head stops. Okay, this is the third hard drive head algorithm. As I said many times, operating systems are very complicated. You need to deal with the memory, you need to deal with the CPU and the file system and these devices like that. I mean, if you don't optimize your hard disk, then if you are doing multi-programming, which even the smallest computers do, then you will have problems. Okay, so these kind of problems exist and they solve partially. Sometimes they are not relevant for our world because I mean, on these computers we don't have any drives, right? We don't have any drives. There are special problems with these kind of computers because for the SSD we don't have a heads, but we have the number of writes problem. If you keep writing to the same sector, that sector becomes bad because there are only a limited number of reads and writes from the SSD drives. So that's the problem with the SSD. We don't have such problem with the hard disk, mechanical hard disk. So each device has its own problem, and operating system has to deal with those problems. Okay, when we come to the error handling, there are many levels of error handling. The earliest one is at the beginning of the hardware level. Okay, the manufacturing defects introduce bad sectors, and bad sectors are one of the main problems with the magnetic hard disks. Sectors do not correctly read back the value just written to them. How do I know that the sector is bad? Once you write it, okay, when you are reading it, your ECC checksum doesn't hold. Your ECC goes bad, and you know that your sector is bad. So what is the solution? The solution is this. For every track, there is a spare sector section. Let's say I have 29 sectors for this track, and I have 2 spare sectors. They are not used at the beginning when the hard drive is manufactured. If one of these bad sectors, if one of these sectors goes bad, I cannot read whatever I am writing to it, then I can replace one of these there. Okay, so let's say sector number is bad, so I took this one and put number 7 there. Okay, so that one becomes 7. Okay, this is one of the algorithms for bad sector replacement. What is the problem with this approach? The problem is
more than 2 blocks being sectors, so you can't place them all.
you mean the number of spare? I mean, you can solve that problem by assigning more spare sectors. But I'm talking about moving this data to there. There is a problem. When you are doing sequential read, when you read 6, okay, to be able to read 7, you need to wait until the disk spins all the way there. Okay, after you read 7, you need to wait until the disk spins back to 8. So there is a rotational delay when you are reading this kind of stuff. Okay, so that's the problem. So how do you solve this problem? How do you solve this problem? The performance issue with moving this sector from here to there. If you move it here to this position, there is a reading performance problem. How do you solve it? Yes. You could move all the sectors that way. Okay. So bad sector is here. 7 is stored that way. Okay. So the issue is solved that way. But moving all that data takes time, and it's the task of the operating system. And it becomes very complicated to keep track of which sector is where. That's why we remember that sector format. There was a preamble and the ECC. That's why you have the sector and this sector and the track number and the other information in this preamble stuff. But somebody needs to remember this. Somebody needs to remember for this solution. Somebody needs to remember that 7 is somewhere else. So you could use another table to store where the sectors are inside the controller's memory. Okay, so that it would know where the sectors are. Another problem with this kind of error handling is that when you are taking the backup, okay, you should not back up these bad sectors because they are marked. And when you are backing up your files, if your file has bad sectors in them, obviously that will create some problem. You need to be careful about those backing up problems. Okay, is there anything that? Okay, so this is a problem with the medium of the hard drive surface. Okay, how does a sector goes bad? We don't know. Maybe there is a problem with the coating, those magnesium oxide coating or iron oxide coating. I don't know. maybe there is a dust particle just stuck on the sector that you want to read or write. We don't know what is happening, but sectors go bad, and this is not the only thing that can go bad. Sometimes your hard drive head, you would ask it to move to cylinder number 9. It doesn't go there. It goes to cylinder number 10. Okay, so because these are mechanical stuff, errors might happen due to vibrations and other. Maybe you are using computer sideways up. Okay, these problems might happen. Maybe there is a vibration inside the hard drive, and these kind of problems might happen. So seek errors caused by mechanical problems in the arm, also problems. In that case, when you go to cylinder number 9, you read your preamble of one of your sectors, you realize that this is not cylinder number 9. This is different. That means that there is a problem with your head. In that case, one solution is recalibration. Okay, the operating system asks the head to move to cylinder number 0. Okay, going to cylinder number 0 is easy because you cannot go beyond cylinder number 0. It is at the end. When you go at the end of the cylinder numbers, it is cylinder number 0. Okay, and from that cylinder number 0, you can recalibrate your cylinder head by going one by one and checking if the numbers are coming back correctly. Of course, you cannot do this recalibration if you have a real-time system. So for the real-time systems, you cannot afford these kind of back sector movements, back sector copying, that kind of stuff. That's why most of the time, for the real-time systems, you don't have any mechanical disks, okay? Because they are too unreliable for real-time systems. They are too unreliable for real-time systems. Okay, any questions about the error handling? These are just, by the way, most of the stuff from the book, I'm just skipping it because the book has lots of other information. You are responsible from all of those stuff, right? You are supposed to read it. Don't try to study only the stuff that I am telling you because I don't have enough time. You are old enough to read a book by yourself and understand it. Okay, another technique with the disk is stable storage. We like RAID because RAID is good. It is becoming blue. I don't like this color. What about this now? Again? Oh, so there is a problem here. Okay. Good enough. White again. Okay. RAIDs are good because they are. If there is a disk drive crash, I can recover my data from the other part of the disk. Also, they are very fast. However, they do not protect against write errors, laying down bad data in the first place. I mean, if I write something bad, I am writing to the disk. While I am writing to the disk a sector, my process crashes, okay? My CPU crashes. There is a problem with the CPU, okay? So if the computer crashes while I am writing to the sector, that sector becomes bad because it doesn't contain valid data. That sector becomes invalid. So they developed this solution, stable storage. Okay. For some applications, no, it is essential to store your data perfectly. When you are writing to the disk, you should write the perfect data, even if your computer crashes while you are writing to the disk space. So they invented the stable storage, and the stable storage, it uses a pair of identical disks. They have two disks, okay? They are identical. So either can be read to get the same result. And when you are writing, you need to be careful. So the situation is this. Two disks doing exactly the same thing. So when you are writing, you should write on both of them, okay? When you are reading, you can read from one of them only. That's okay, okay? When you are reading. But the thing is that, remember, we are using stable storage for we are using stable storage against write errors. Okay. Okay. When you are writing, okay, these are your disks. Before writing anything, if your CPU crashes, no problem, because your disk did not get affected. But when you are writing to one of your disks, if your CPU crashes, okay, this becomes bad, but I have the second disk, okay? I have the second disk. And so I can handle this case, because I know that it crashed when I was doing this disk write, so I can get my data from the second disk. I wrote my data, everything went perfectly. Before writing the second one, my CPU crashed. So in this case, I have the new data and old data. There is an inconsistency. What do I do? So in the next time, I would copy this data from there to there. Right? So no problem. If my crash happens here, then it means that I have the data in the first one. If my crash happens here, there is no problem with this one. So whenever your crash happens, it doesn't matter. I can always have the valid data. Either it is old or the new. Okay. Old is valid, new is valid, but when you are writing to the disk and your CPU crashes, that sector becomes invalid. That sector becomes invalid. So this is a very popular technique used by the databases or some other data critical task. When you are writing a unit to the disk, they say that you either write it to the disk or you don't write it to the disk. So you don't make it, your data invalid by writing it halfway through. So this is called stable storage. It has these three steps: stable writes, stable reads, and crash recovery. And the stable writes